Was it tried? The title
is on stochastic travelling waves. And so I don't really want to thank the organisers because when I first looked at the programme, I was the first speaker on Monday morning. And then when I looked, I thought, terrific, I can have a nice relaxed conference. And then the next time I looked at the programme, I was the last speaker on Friday. And you need to have somebody very relaxed with lots of movies and jokes. And if you can't do that, you should keep it short. So I'm going to go for the short option. And my talk is quite related to James Nolan's talk. It's a report on work with a graduate student, Nick Woodward. And almost all of what I'm going to say, apart from a few bits, is it will be in his thesis. And it's on one-dimensional travelling wave equations. And I realized after listening to James' fantastic talk on Monday that I'd given the student the wrong problem, and I'd also given him the wrong tool to solve the problem. So just to make a comparison, here we're in one dimension, in case you weren't in that Monday morning talk. And F is going to be one of these KPP type or bistable type nonlinearities that has travelling waves. And James's talk looked at F of U and X and had some, oh, hi. Oh, is it not going?
Mic on?
I don't know how to switch it on.
The red light.
The red light's on, yeah. I'll speak a bit louder. James's talk put some randomness into the F like this. So he had a fixed random inhomogeneity in space, which is probably, and he said there were lots of physical or problems for which this was good motivation, although he didn't list them, but I believe him. Whereas being a novice to this area, I chose to do it this way. But my feeling is that that there could be some similarities. So I think in the dispersive equations, also some of the models, is this right, Arno, the noise is modelling inhomogeneities in space. But you would choose a driving Brownian motion to give you the set of tools that you are familiar with. Also remember for these equations with the travelling waves that the action is all on the wavefront. So even for Jim's model, the wavefront moves along and it meets a fresh bit of space where the noise is perhaps independent of the bit that it met before. So there's some more similarities to having a driving noise that's evolving in time for this sort of travelling wave thing. Anyhow, that's what I asked him to do. So let me just quickly run through the different types of F. So there's the KPP one. So F and G are going to vanish at 0 and 1. So that all my solutions will be trapped in between 1 and 0. And so the KPP type will be something like this. And then that leads to travelling waves that move to the right. And there's a family of travelling waves with some slowest speed. So we'll label them as KPP. And then there's the bistable ones, which look like this. And they have travelling waves. They have a unique travelling wave, which can either be moving to the right or to the left, depending on F. There's one travelling wave. And then there's I'm going to talk very briefly about the unstable case. So that's where you flip these over. So why is this called bistable? The front of the wave is being squished down, and the back of the wave is being squished up. So in the unstable case, it's the opposite. So what happens there, the front of the wave is being lifted up, and the back of the wave is being pushed down. So you get solutions that look like this. Where you get a large flat patch at this value A, and then below it, it's zooming off to the right, and to the left of it, it's zooming off to the left. So they don't normally get into the books on mathematical biology because they're not so interesting. So those are the three types of F. And G, I'm just going to choose to vanish at 0 and 1. So the picture of G will be like this. And by these pictures, I mean, I'm not going to consider the, what's it called, the ignition one, where this can be 0 for a while. These are strictly positive derivatives at all the endpoints. So they sort of generically look like this. And then I asked him to look at G of U, circle dB, for a single Brownian motion. Of course, you might prefer a spatial case. And of course, this is a sort of warm-up for this. I still think this is interesting, and I was relieved when my friend Jonathan Sherratt, who's a big mathematical biologist, said, oh yes, single Brownian motion, you should call that seasonal noise. So you have some quantity that affects the entire wave. Like, I guess he's thinking of sort of temperature varying over the seasons. And so if you're plotting some population spreading over many years, the entire population is suffered by a single noise. So I still think there's some interest in this. And I will talk mostly about this, but the main result does extend to this case. And with a bit of luck, the rest will. So that, I think, is the end of the... Oh, should I use Stratonovich or Ito? Well, of course, that's a modeling decision. I thought for this seasonal noise, it would be more natural to model it as Stratonovich as the limit of some sort of non-white approach. Anyhow, you can quickly change it to Ito, adjusting the F suitably. But if you do that, you get this strange phenomenon that you can change the type of F. So if you change G to an Ito noise, F changes to F plus a half GG prime. And if F was originally one of these types, it can flip to a different type. So it's easy to come up, even just with the pictures I've drawn. You can flip from KPP to bistable, and you can flip from bistable to unstable. So what should you do? James, you should probably tell me if I'm saying anything wrong. But my guess is that what's going on is that you should use Stratonovich noise, and then all the theorem should say that the stochastic, a lot of the theorem should say that the stochastic behavior is similar to the deterministic behavior, existence and numbers of traveling waves and domains, but that unfortunately at some point I'm going to start taking moments, and then I want to use Ito noise. So I think I'm going to use F naught for the corrected F. And sometimes my assumptions will involve F, and sometimes they will involve F naught. But the types can change between F and F naught. Okay, now the reason we used the wrong tool was that we got stuck in 1937, which was, I think that was the date of the original KPP paper that James mentioned. And the original paper has this key idea that if you start off with a Heaviside function, the solution starts very steep and it gradually gets less and less steep. So it stretches. So let me just, if you haven't seen it, let me just quickly go through. So you have to center the wave. So I'm going to let gamma t be the first x at which u of t and x gets less than or equal to x. Oh, right. Let me tell you whether I'm going to work in these two cases. I'm going to start off with a single Brownian motion. And there's a big technical advantage, which I knew my student would like, that the solutions stay monotone decreasing. Whereas if you have a spatial time noise, they will not stay spatial decreasing. Okay, they will still go to 0. And so this marker of the wavefront is pretty good for this case, but is less good for this case. It'll be here, and then if the back of the wave jumps below, gamma will be discontinuous. So, of course, it doesn't really matter what marker you use in all these theorems, but it's a technical point. I don't know whether... I know that gamma t is a semi-martingale for this case, and I don't know if it's a semi-martingale for this case, whether the jumps ruin that. I'm interested to find out. Anyhow, so that's the marker. And then you center the wave at that marker. And then the key Kolmogorov lemma is that if you plot u twiddles t of t and x. If you start off at time 0 with a Heaviside function, and then as you run it, it just starts getting flatter. Oh, I should flatter and flatter and flatter and flatter. It stretches. It becomes more stretched. Is that right? So this is t increasing. It goes up here and down here. And so there has to be a limit because it's increasing to the right and decreasing to the left. And then you just have to check some compactness that it doesn't go completely flat. So this stretching plus some compactness tells you that u of t converges to some limit, and the limit will be a travelling wave. So that's the idea in the deterministic. And a little thought convinces you that that should probably go through in the stochastic case when you add g. And the answer is, so if I want to give a very short version of the talk, the answer is that it basically does, and that it looks like it will do in this. So have I got any more time? Because I think the football players could leave now. But if there are some non-football players, I'll give a few more details.
Too late. Results already up 1-0.
Thank you, John. Okay, the tennis players then. Now the travelling wave experts can relax, because I'm just going to follow in the footsteps of Fife and McLeod, who give a nice way of seeing this. And then when you see their method, you see that it should work in the stochastic case. But if you haven't seen it, it's very cute. So Fife and McLeod said you should look at this in phase space. So you should look at the derivatives. It's the derivatives that start off very steep, very, very negative, and then they gradually get less and less. So you should define p by that the derivative u prime is p of u. Let me put in all the t and x's. U prime at t and x is pt of u, t, and x. So at each height, u of t and x, you can read off the derivative, and p is the function that does that. Okay. So I suppose it's u prime of u inverse. And you can do Ito's formula on that. And, well, let me tell you what it gets. You can write out the evolution in p space. So just this equation here becomes in p space. Oh, I want to make my derivatives are all negative, so let me define it to be minus so that p is positive. It becomes, a little miracle occurs. Have I put the plus here? Okay, it becomes that. So it becomes a interesting operator here. But this is simpler. So this has become linear. Whoops, have I missed off the people? This has become linear. The nonlinearity f comes through as inhomogeneous but linear multipliers here. So the p is defined on the height. So p is defined in between 0 and 1. And they suggested that you should look at this to study this result. So what's happening here is that the slopes are very, very negative. So p is very, very positive, and they gradually get less and less negative. So if you plot the corresponding p curves, they look like this. And now you see that what corresponds to stretching there is just simply monotonicity in p space. And to make it work, you just need a comparison theorem. You need a comparison theorem that if you start off two solutions, one above the other, they stay coupled above the other. So if p naught is bigger than q naught, two solutions of this, then pt stays bigger than qt for all t. Okay. And okay, so it's got a nasty p squared Laplacian p, but you believe that it should work. And once you have this, if you start off from the Heaviside function, the Heaviside function has an infinite derivative. So it starts off way up here at infinity, and it just slowly goes down. So once you have this, it implies that if P naught is infinity, then PS is bigger than or equal to PT, S less than or equal to T. In other words, the corresponding P curves are just decreasing. So I've sort of redone that picture in phase space. And now you realize, oh, this is going to work in the stochastic case. In the stochastic case, if I stick to Stratonovich G, I'll just get an extra term here with the corresponding G's. Whoops. Whoops. Yes, G prime P minus GP prime circle dB. And comparison theorems like this work very well for stochastic PDEs. So you should get the same comparison theorem, and that's still true. And you just have to work a little bit more careful here. When you work through here, you get that these are stochastically ordered. Let me remind you why. So why do you not get this? Well, you start off with P naught. P naught is identically equal to infinity. So that is definitely going to be bigger than or equal to PS coming down. And you then run you run two solutions, one started from P naught and one started from PS for a further T. But you run them with the same noise so that you can apply this comparison theorem. The two results will still be coupled, but that's not the right noise. You only get versions. You get something here that is equal in law to PT plus S, because you've used the same noise here from S plus T is to from 0 to T here. So you don't end up with the true solution being coupled, but you end up with version, things that are identical in law to the true solution and which are still coupled. And that's what stochastic comparison means. I.e., so this means, i.e., there exist versions, copies of these as random variables, which truly are almost surely coupled. So I'll write my versions as P hat. Okay. So that's a stochastic ordering, but that should still be good enough. You get this picture in the stochastic case, not for the true solutions. So this is not T equals 1, 2, 3, but this is a copy of P1, and I can find another copy of P2 at which it looks like this. And so if I'm just interested in convergence in distribution, I don't care if I use copies. These still converge up to something, and it should still all work. Okay, now there are some difficulties with this comparison theorem. You have to deal with the infinite entrance law, and you have to deal with this nasty nonlinearity. But the key problem is, what are you going to do if you want to use dw, circle dw, x and t? Then you're going to have solutions that look like this. And the corresponding p's, the slope at a given height, is a multi-valued map. At a given height u, there are plenty of slopes. Now, I see Michael nodding at the back there. He should say, you should just go ahead and prove this with multi-valued p's. But we don't have the courage. But there is, sort of still in the literature, there's a standard way to take this as your inspiration and do it not in p space, but back in u space. So you're guided by this, but in fact, you can do it all in u space, and then you can cope with these solutions that are not strictly decreasing. So that's the next bit. Okay, so here are some of the definitions back in u space. So you work in u space. So now, in other words, that just tells you why it should work, but you don't actually use it. Although you can prove comparison theorems, so you could do the spatial case, the one-dimensional case. So here we are. If I have phi c, I'm going to call phi crosses psi. Phi crosses psi if, well, rather than write the definition, I'll just draw phi crossing psi. Here's psi, and here's phi, It starts off below. Once it gets past, it stays past. So there's a picture of phi crossing psi, and you can work out the definition. So these are definitions. And then you can say phi is stretchier than psi, or more stretched than psi, if all possible translates of phi cross psi. If tau a phi, by which I mean phi of dot minus a crosses psi, for all I. So somehow, no matter how I shift phi, it must only cross at one point. So you can check that if you were back in the case of strictly decreasing functions, this is exactly equivalent to the corresponding p's being one above the other. It's just a way of writing it over in the space of shapes. And now the key lemma is how they do these things. And this is the lemma from McKean's original version of the Kolmogorov. Where am I, on the wrong page? That if you go back to your U0 equation, if U0 crosses V0, if you have two solutions where U0 crosses V0 at time 0, then it will cross at all times t. So if you have two wave profiles where one just crosses once the other, that's preserved as a property at all times. And that holds whether you work with a single Brownian motion or whether you work with a spatial Brownian motion. So this is the key lemma, which is sort of well known. You have to check that it works still with the noise, but it's really a path by path. You can check it path by path. It's not a random thing. And then you just read off the corollaries. So the corollary 1, and the sort of key corollary, is that if you start off with the Heaviside function, so let me do it in the two different cases, because the conclusions are slightly different. If you start off with g of u circle dB with a single Brownian motion, then if u0 is the Heaviside function, as time progresses, it gets more and more stretched in this sense. The law of ut is stochastically more stretched than the law of us, if t is bigger than s. So what does that stochastically mean? Now we're really in the sort of Linville stochastic variables. We have an underlying space of functions with a partial order. Oh, it's not quite a partial order, it's only a pre-order, but that turns out to be enough. And this is stochastically bigger than. In other words, there's a version of ut which is almost surely more stretched than us. So I should write that. I.e., there exists u hat t, which is more stretched. Than u hat s. Okay. In the dwtx case, you get almost the same thing, but a subtly different. Again, start up with the Heaviside function. You get for all a, there exists a version of the translate of ut, which crosses a version of us. And it's just interchanging parameters here. So for each possible translate, I can find a version of the solution which crosses only once a previous version. If I could do it simultaneously for all a's, I would have this. But you get the same ingredient, that all possible translates obey this. But it means that this is not actually a true stochastic ordering. There's not an underlying space with a partial order on which the laws are stochastically ordered. But it has all the same ingredients, so I'm optimistic that it leads to the same conclusions, that the things are converging. Okay, I'm nearly finished. So now you can read off some consequences. So this is a soft tool, right? You can't expect too much from this. what do we get? Corollary 2. So now I need to combine it with this compactness idea. So I'm going to go back at the cases. If F0 is a KPP type or bistable type, and U0 is the Heaviside function, then the solutions converge in distribution to some limiting law. And this is the law of a stationary travelling wave. So nu is the law of a stationary travelling wave. Did I forget to define a stationary travelling wave? I did. Okay, there's no difficulty here. It just means that the centered solution is stationary in time, is a stationary process. Okay, if you started off according to nu, the centered solution will be a stationary process. That's what I mean by a stochastic travelling wave. Okay, and that's what you would get. So you need some compactness. The things are getting flatter in this stretching sense, and you just want to make sure they don't get completely flat. So just slightly surprising is that you can also do it in the unstable case. In other words, even if the underlying F0 is unstable and would normally split the thing apart, the noise stabilizes it, and this limiting guy is coherent. But it's not that surprising once you've drawn the picture. So what can happen? You've got this picture as in Kolmogorov, but now they're the versions. So they're coming down, getting flatter and flatter. All that can happen is, the only thing that could go wrong is that you get a large flat patch stuck at this intermediate level A. But if I make sure my noise G doesn't vanish at that level, large flat patch, which would ruin the deterministic literature, will wobble up and down and will eventually disappear. So it's an example. We all know toy examples of SDEs which are stabilized by noise, but this was nice to have a real problem that was stabilized by noise. I don't know, it's very interesting. Jonathan was interested by it. It would be nice to know how stable it is. So you need some compactness, and let me make some comments on the compactness. All you need is compactness here. In other words, you need to know that it doesn't get flatter and flatter. So we looked at ut of x, 1 minus ut of x, integrated over the whole of the real line as a measure of somehow the width of the interface. So here we go. It's going to look something like that. This will give you some measure of the width, because the front of the tail doesn't contribute, the back of the tail doesn't really contribute. You're getting the guts of this integral from here. So in the bistable case, you can just hit this directly. And shall I call this guy L? L for the length, but it's some measure of the length. In the bistable case, you can just check that the expected value of LT to some power P is bounded in T. And you can just do it using Ito's formula. You just develop this. And on the right-hand side, you see that there's a negative contraction term that keeps you squashing down. In the KPP case and in the unstable case, you have to work. It's not so that doesn't work. So you just have to rely on the original equation and get what you can out of it, which I've rubbed off. So what's the answer? In the KPP case, you can prove that the first moment. So this is for some p bigger than 1. And you can get the first moment is bounded in T. That's enough to stop it getting wider and wider. But in the unstable case, this actually grows. So somehow, in the unstable case, it is getting wider, and then the wobbles in the flat patch suddenly crunch it up again. And then it starts to get wider again because of the deterministic, and then the wobbles crunch it up. Sufficiently that this length is not bounded in T. But maybe if I put a half power there, well, I don't know. What is the right power? I'd like to know. But these things aren't tractable enough to do much sort of Ito calculus on. Okay. Am I going to say anything about that? Last page. Yes, so how do you get these the more tricky cases? All you've got to, all we could work with was the original equation. And now, if I look at the centered equation, you get an extra term. The centering gives you an extra term where it's driven along according to the wave marker. So you have to check that this is a semi-martingale, but it is a semi-martingale. And I think most of the technical problems came from the fact that it's hard in the stochastic case to decouple these. You'd like some information about gamma. And this is one of the few ways you can get some information about gamma. Gamma, its semi-martingale decomposition is awful. There's all sorts of things you don't know anything about. If you could decouple it from this, you would get some information, but they're very dependent. So all you can do is integrate over blocks. So if you integrate this over the whole of R, then this guy decouples, because you can integrate the derivative and get the value of u at infinity minus the value at 1, which is minus 1. So this guy decouples just to gamma of t minus gamma of naught. And you start to get some information about gamma of t. And this guy gives you some information of the sort that you're interested in. Well, you wanted u1 minus u, but that's roughly what f0 looks like if it's of KPP type. So if you want the first moment of this guy, you just have to estimate the first moment of everything else. And you can get some crude bounds on the wave speed just by comparison with linear equations. So that gets you the first bound here. In the bistable case or the unstable case, you don't. You just get information on the front of the wave. Well, that's okay. So that would be the front of the wave. That would be a sort of integral on this bit. And you end up showing that this expectation is bounded in T. So that's the part of the wave from the centering point forwards, and tells you there's not too much here. But it's weighted if there could be a large flat patch in A here. And you can do the same with the back of the wave, and you have to eliminate the flat patch in a rather crude way, just sort of saying, look, the noise is non-zero there, and so it has to wobble. Okay, I thought that would be it, because really to get interesting results, you have to do what James was doing in his talk. You have to really there's no really hard estimates here. You have to do some hard estimates, and for the KPP case, you've got to use the front of the wave and model it carefully. In the bistable case, you have to use the squishing property. But you can get just a little bit more out of this soft tool. So you've got one more result. Corollary, what am I up to for? Well, this idea of stochastically ordered things is used by the particle systems people a lot. They start off with all ones, and that's a maximal entrance law for their particle system, which can be ones or zeros. So they use it a lot. And so you get this corollary for free. If your initial condition is more stretched than the heavy side, but less stretched than this stationary traveling wave, then for free it must converge to the traveling wave, because it's sort of squashed between them. The heavy side will gradually become less and less stretched and converge to nu. So if this poor guy is trapped in between, it must converge. So this is for free. That there are other initial conditions. But how on earth can you tell whether an initial condition, it's obviously more stretched than the heavy side, but how can I tell whether it's less stretched than this station? So this is useless, I think. It tells you that there is a domain of other initial conditions that get attracted, but you just can't identify them. So more interestingly, you would expect that if you have an initial condition that is trapped, by which I mean that it is identically 1 for a while. Oh, I'm in the decreasing case. I'm in the case of a single Brownian motion. And identically 0 after that. So it's trapped in between some A and B. that this should also converge to the limit you get from a heavy side. After all, it's not so far from a heavy side. If those aren't converged to nu. But you can't, I was suspicious that you could say anything about these because you don't know that these are getting more stretched. There's only one solution that you know is getting more stretched, and that's the one from the heavy side. But it turns out that you can prove this. So then the law of U2 converges to the same one you would get from the heavy side. Oh, except there's a drawback. This soft tool only gets you this. That the Cesaro averages converge to nu. Well, it can't be true, right? But I think I won't show you why. Anybody who's interested, I'll show you why you lose that little bit there. But essentially, you can. The point is that you can use the fact that nu is the minimally stretched solution to get this. If it's trapped in between two heavy sides, it remains trapped in between two heavy sides forevermore. So if it settles down to something, somehow it must settle down to a steady state, to a stochastic traveling wave, but it must be a more stretched than nu. And now you look at wave speeds, the two wave speeds. The wave speeds are identical because it's trapped between two copies of the heavy side. And there's a formula for the wave speed in terms of the steady traveling wave. And you stare at those two formulas. They can only be equal if the limit of these guys is the same as nu. That's sort of 10-second, giving me time to go and see some of Andy Murray. Okay, I think that's all I want to say.
Questions?
Right, we can go.
Sorry.
I
Is
did.
it okay if I ask a quick question?
Go on.
Is it clear, or is there a simple explanation for why there's a comparison principle for these? Is there a maximum principle?
Krylov has a paper where he does maximum principles, but the normal proof for these SPD is to take the difference of two solutions, positive part of the difference, and just use Ito's formula and use it. So that works in most cases.
Have you looked at small noise asymptotics of the speed?
No. But aren't there some, you should know, there are some physics papers.
Right, I was just wondering how it would work out in this case, yeah.
I haven't thought about it. I actually wanted something that was not small noise, but there must be much about many other tools to use with small noise.
No more questions? Let's continue. And let's thank Bill and I